This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning. So today we're finishing up with kernel methods. We'll return to them briefly later on in the semester when we talk about PCA and unsupervised things. We'll talk about a particular kernel method. We'll make use of some of the stuff from today then. But today is the third and last lecture on the topic. So what we've covered so far was the SVM, right? So we derived the formulation for the hard margin SVM, which doesn't like to have errors. So it requires data to be linearly separable. And then in the second deck, we did the soft margin SVM, which permits inseparable data, data that isn't linearly separable. And in doing that, we also set up some things for today. So we also did the dual formulation of both the hard and the soft margin SVMs, which is an equivalent way of solving the SVM. And it uses this cool machinery from optimization called Lagrangian duality, which is about kind of converting constrained problems into, with one optimization to roughly unconstrained problems with bi-level optimization, but it also means you can swap the orders of optimizations and then get an equivalent formulation with a different number of variables maybe. So today we're going to sort of finish this set of ideas with kernels. And the ideas in this lecture don't just relate to the SVM. They're very, very general. So there's a lot of methods that are kernel methods. And I'll sort of have I'll talk about that a little bit, and I'll kind of give some pointers. Okay. All right. So we'll talk about kernelization, which is basically just running the linear method in a feature space. So it's a lot like basis expansion, except that if we look at the dual formulation, we notice that we only need dot products. So a kernel just is like a dot product in a feature space. That's what a kernel is in the context of this topic. And then that sort of gives you the idea that you can do learning and you can do feature mapping as like separate modules. And we can sort of think of a modular approach to kernel methods. And so I'll talk about that. And I'll talk about different kinds of feature maps that work and different kernels that work. And I'll give you some tools that can be used to recognize when a learning algorithm is a kernel method. So it's called the representer theorem. And another tool which is called Mercer's theorem, which is when you can recognize when something is a valid kernel. So lots of tools that are useful, but also very, very cute ideas as well. Okay. So first step is to make the SVM more nonlinear still. Okay. So in the last deck, I sort of said it doesn't have to be linear. The SVM will run for nonlinear data, but the model itself is still linear in the original space. So it's still a linear method, right? Now, the other idea that we're now going to combine with it is this idea of training a linear method in a feature space. And maybe we're going to add lots of features. And so if we add lots of features and we run sort of the SVM training in that feature space, then that's going to correspond to something nonlinear and more appropriate in the original space. That's what we're going for. So I'm kind of mashing up ideas from the last deck, what we're up to, with ideas from deck 4. Okay, but it's not just going to be a mashup with nothing new. There is going to be a whole lot of new stuff. Okay, and you might have seen some of this before, but I'm sure I'm going to be showing you some new things as well. So this is kind of the picture you have in mind when we're doing basis expansion. I have a problem that clearly isn't appropriate for a linear classifier. But if I can training a linear classifier after applying a feature mapping phi, right? So adding features, mashing up features as well. If I can have something nonlinear, that dotted line might correspond to something appropriate in the original space that's going to work well. Okay, but I've still got to choose this phi. So it's not completely magic. You know, we've still got to do some kind of model selection or grid search or something over the kinds of phis we might use. Okay. So this is kind of reminding of basis expansion, a little bit from deck around 4. So suppose this is our problem. We've got red and black. We've got sort of squares and circles and squares. Okay. And we'd like to find a boundary that separates them. And maybe this is the best boundary you could come up with that's linear. Not so good, right? It's making lots of mistakes. But if we add another feature, for example, the radius from the origin, or the radius squared from the origin, so sort of we've got a bit of our original Cartesian kind of coordinates, and then we've got a bit of polar stuff as well. Then, so x, right? So x3 is sort of the distance squared of a point from the origin. Because when we look at this, the red points are kind of around the origin, aren't they? So it looks like that might be a good feature to add. Then suddenly we've got a third coordinate, and you can see the data lifts up because we've gone to 3 dimensions, and now we're kind of like lifting the data up along a parabola, a paraboloid, like a bowl, and you can see now all of the red circles are now low because they're a small distance from the origin, and all of the black squares go high up because they're further from the origin. So this is supposed to be not necessarily not a line but a plane, kind of cutting across the x3 equals some thresholds. Maybe we're looking along the plane, and that's why it's not a plane looking thing, but it should be a plane. This works better. Now it's still not perfect, and I want to get that message across to you. It doesn't, just because we do a feature mapping and we have something nice and nonlinear in the original space, doesn't mean that we're perfectly classifying things. And remember from our discussion about regularization and overfitting, we don't necessarily want to get everything right in the training set. Right? Sort of doing really, really well on benchmarked data sets, getting to 100% doesn't always make sense. That shouldn't always be the goal, right? So you can imagine we might make some mistakes on things on the boundary, and that's fine. But we're doing a lot better than we were. I'm claiming it's linearly separable. Doesn't really matter if it is. Okay. It's more linearly separable. So the workflow for basis expansion and for adding features is as follows. You choose the kind of linear model and learner you want. That's what we've done so far in this topic. And then we're choosing some feature mapping, and that might be using domain knowledge, or it might be through a bit of trial and error. And then we map all of our training examples into this feature space, phi of x, and then we train our learner on that transform data. So that's nice and clear. We just do these things in turn. Now I'm saying it's naive or overly simplistic because what we're going to see for kernel methods, they're not just any old learner that we can run in a feature space, because we can run any learner in a feature space. There's nothing special about that. But kernel methods are special because we don't actually have to explicitly map the data into the feature space. We don't have to go through that step, this kind of third step. Because what turns out to be important for kernel methods isn't the feature mapping of the data, it's the dot products of the feature map data with each other. And if you choose your feature mapping carefully, the dot product might be cheaper to compute than first doing feature maps and then doing dot products. Now, it's not obvious why learning algorithms might only need dot products. You might design a learning algorithm that only needs dot products, that's fine. If you sort of look at deck 1 of this topic, it's not obvious that the SVM only needs dot products. But towards the end of deck 2, we saw this dual formulation, and I kind of had a little forward reference there where I said, look, the x's in the formulation of the dual only enter via dot products. And we'll see that. We'll see that in the next few slides. Okay, so it might be that some feature mappings have really cheap dot products to compute. But the thing is, what if I'm using a feature mapping that has it sort of exponentially blows up the number of features? That's going to cost time and space to compute those feature maps. Also, if we were doing the primal formulation of the SVM in a really, really high-dimensional feature space, suddenly we've got lots of parameters. W has lots of components, and we're going to need lots of data to fit a W with lots of components. So for computational reasons, we don't like just doing the feature mapping, but also for statistical reasons, we don't want to have too many parameters by going to a higher dimensional feature space. So what's really cool about this topic is we kind of avoid both of those things, even when using infinite dimensional feature spaces. So we'll get to that. Okay. And so this is the thing. This might be impractical or impossible, but it's also not necessarily good for generalization if we don't have a lot of data, which is a perspective I don't say so much in the slides, but I'll say it in words now. Okay, so this is the dual formulation of the hard margin SVM. I could have easily put on this slide the soft margin by just upper bounding each of the lambdas, the dual variables, by C. Wouldn't have changed anything about what I'm talking about. I just want to have something on the slide. Okay, so this is this sort of weird looking dual formulation. It's hard to interpret by looking at it completely what's going on. But this is the training process, and from the lambdas, we get the ability to make future predictions by the second display, the second equation. So that's this here, right? So we can make predictions like so on a new test instance. So that's cool. And there's also a way of finding B, of course, as well, which we talked about. So that's the dual formulation. Now, notice, and I kind of mentioned this last time in passing, but we didn't use it for anything. Today we're going to use it, that in training, we don't actually need the X's at all. We could have thrown them away as long as we kept their pairwise dot products. So this is similarity. This is a form of similarity between them, and that's all we actually needed. So if the X's were enormous, that might not matter, as long as we've kept the dot products. And then likewise, when it comes time to making predictions on a new test point, we also don't actually need the X's anymore, the training X's, as long as we have a way of doing a dot product. Okay. So that's sort of what we're going to build on. Okay. And by the way, as a forward reference to later in the deck, this looks like a coincidence, but it's not a coincidence. It's a conspiracy. There's this thing, the representer theorem, that I'm going to state, but I won't prove or anything like that. It's quite, it has a lot of heavy maths behind it from functional analysis. But the representer theorem, if we had applied it to the original formulation of the SVM, it would have told us that this would have happened. It's amazing. This is not a fluke. And so for other learning algorithms that aren't classification, there might be regression, there might be dimensionality reduction, there might be something else, you can actually apply this thing called the representer theorem, and it will tell you that this would have happened, that you only needed dot products. So before you go through all of the pain of the dual formulation and everything, you can kind of peek ahead and see if it's going to work out or not, if you can make use of what I'm about to talk about. So that's pretty cool. Okay. So if we're going to do basis expansion with our previous DEX ideas, what the previous slide becomes is this slide. Instead of running things on X's, we're going to run things on 5X's, some feature mapping. Okay? And we're only going to ever see dot products of these phi's. Okay, so we only need dot products. So this is, just to spell it out, this is the dot product, right? We've been using them quite a lot. Here's the dot product if the original dimension is M, and then if the new dimension is L, right, this is what This is what it looks like. So we apply phi, and then after applying phi to each instance or each vector, we get L components, right? And it might be finite, it might be infinite, whatever. We just get a whole lot of components. And we can do dot products in that space too. And so let's have this definition, because we've got dot products everywhere. Dot products are feature mappings. Let's, call that something. Let's call it a kernel. And like I said previously, this is a different kernel to other kernels, right? This is not the same kernel as, say, in a CNN. This is not the same kernel as in linear algebra. This is a kernel that corresponds to a dot product after a feature mapping of two things. So this kind of kernel has two arguments. It's a bivariate function. That's fancy for saying it's got two inputs, right? And it's got to be it's not just any bivariate function. It's got to be a dot product. There are rules that a dot product has to have. For example, it's got to be symmetric. So it shouldn't matter if you have U or V, well, as long as everything is real valued, that is, but yes. So that's that's a kernel. And let's look at one to motivate the kernel trick, which is, think of the kernel trick as some terminology, right? The kernel trick corresponds to a particular idea. And so this slide is motivating the kernel trick with an example. So for some phis, it's much faster. There's a shortcut to computing the kernel. You don't have to first do phi and then do dot product. You can do a shortcut. So let's do that for a particular simple feature mapping. So suppose we've got our two vectors u and v. Okay, and they're actually super simple vectors. They've only got a single component, u1 and v1. Okay, so super simple and contrived. And then let's imagine the following feature mapping. So this would allow us to get sort of quadratic form decision boundaries, having a feature mapping like this. We've played with this kind of feature mapping before. Let's take our feature, and we'll leave it as is, but we'll maybe like scale it by some constant. Doesn't really change the shape of the boundaries we can get. Let's also add a constant so that we can get offset terms. That's pretty handy, yeah. And then let's also square our feature so that we can get these like quadratic forms. So that's our feature mapping. So let's think about what dot product under this feature mapping looks like, and then think, is there a shortcut? So we can apply it to one vector u and one vector v. They're very simple vectors. And we can get these new vectors, right? Then we can take a dot product, and it looks like this. Now, there's a shortcut to computing this. It involves just taking the original input points, not mapping them via phi at all, adding this constant c, and then squaring. So we're sort of doing things in a different order. We're doing a dot product first, and then we're doing something to that. But the kernel trick doesn't always look like that. Sometimes it's a different operation you do to the original vectors. But the pattern is you're choosing feature maps that have kernels that don't require you to do the feature mapping first. Okay, and so just to spell it out, if we wanted to define the corresponding kernel for the feature mapping we had, this is one way of defining it, or we could have defined it this way, but they're the same. Okay, so how does this save time? Well, I'm counting arithmetic operations, okay, and I'm trying to pre-compute things that I could pre-compute. To do the feature mapping, and apologies for color blindness. So here I've got these like annotations here. They happen to be in green, but they're unambiguous. I'm doing two arithmetic operations here. So one, I'm squaring a feature, right? I'm doing a float times a float. And here I'm also doing another multiplication. So I'm doing like u times something I've pre-computed. I could have pre-computed this before I started. Square root of 2 times c, that's already saved. And then I do one more multiplication to get this. And then there's plus 2 more multiplications to get this feature embedding. And now I can save these three things, right? I've got these things saved in memory. And then to form the dot product of them, I've got roughly 5 more operations. I mean, it depends how you do it. If you're using, some specialized hardware, it might be less. But we're doing 1 and 2 multiplications, maybe a third. You could have pre-computed that, I guess. So 1, 2, 3. So we're doing times, 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 and times, times. And then we're doing 2 additions, right? So that's 5 more operations for a total of 9 operations. Big deal. That's not that much, right? But it's a number. So how many operations do we have to do it a different way, right? So to do it the direct way, we've got 1 product, we've got 1 addition, and then we've got 1 more product, squaring. We're squaring these things. So that's roughly 3 operations. A lot less, but imagine that we had not just x squared here, but imagine we also had x cubed and x to the 4 and x to the 5, and we went up to like the 10th order. There would be a way of writing this like this, where we're essentially starting to look at sort of exponential versus linear. That's the kind of the calculus of this. So the difference isn't so big here because it's a very low order polynomial. But if I'd wanted even more flexible decision boundaries, I would have been looking at a lot more expense compared to this shortcut. So this idea of having a shortcut way of calculating a kernel is called the kernel trick. It's just pointing out that if you only need kernels of things, why ever even write down the feature mapping? Also keep in mind, this thing could be quite expensive to write out space-wise eventually. If you've got a lot of training data and you're wanting to do feature mappings for all of it, it starts to get expensive to even save it. But if all we needed were dot products between things, maybe we can save on space too. Okay. So more generally, the kernel trick, just to sort of put it all together, we've got training examples, and we've got sort of this kernel matrix, which is computing the kernel value for every pair of examples. And you may not need to do that ahead of time. It depends on what algorithm you're using to actually train. But often you would just compute the whole kernel matrix, which obviously gets expensive if you have a lot of data. Then it's the kernel trick if there's a shortcut for computing this. So not all kernels have a shortcut. So you could be using a kernel method without using the kernel trick. It just sort of depends. But a lot of the common kernels do have a kernel trick for computing them quickly. Right? So the kernel trick doesn't involve doing these things. Okay. And it could be impractical not to use it, or it might be infeasible. And in fact, the most common kernel, which I'll show you in a bit and we'll talk about, is the RBF kernel. It corresponds to an infinite dimensional feature space. So we'll talk about that in a bit. So you couldn't do it any other way. You have to use the kernel trick. So all I've done in this slide is taken our last slide with the SVM formulation, and I've replaced phi.phi with just k. So I'm doing like these very little changes, right? You can kind of see it in slow motion. It's not changing very much. So now we've got kernel SVM. Yay. This is the kernel hard margin SVM. The kernel SVM usually refers to the kernel soft margin SVM, and we'd have a C upper bounding here. So that's kind of highlighting the change. So if you compare now the SVM, say, with a neural network for how they get nonlinearity, since these are 2 examples of learners, 2 really important classes of learners, what the neural network is doing is it's using activation functions to give us some nonlinearity, and it's also using composition, so taking outputs of layers and feeding them into inputs of layers. So when we look at those like enormous CNN models that I was kind of just flashing on the screen, when we're talking about CNNs for like computer vision or for natural language processing, you're getting lots and lots of layers, and you're having these like potentially nonlinear, well, you have to have nonlinear activation functions, right? So that gives you nonlinearity. For the SVM, we sort of have one layer of nonlinearity. So it's just the feature mapping or the kernel, they're the same. Feature mapping and kernel are almost the same thing, right? One feature mapping gives you one kernel corresponds to one feature mapping. That's how the SVMs get nonlinearity. And you could sort of, I mean, you can see I'm using I'm sort of using phi's here. You could be doing this as well. But what I haven't written here is you're also applying phi or some other symbol to activation functions, right, as activation functions after the weighted sums. So on the left, activation functions are applying after weighted sums of things. So it's like a generalized linear model if you've done some stats. So in stats, we talk about link functions and generalized linear models. So we apply transformations after weighted sums. Here we're doing transformations right at the start, and that's the only transformation we can do. Okay, so here's a little check-in. Let me see if I can get rid of that. Go away, thank you. Okay, so does any method that uses a feature space transformation, does it necessarily use a kernel? What do you think? It's okay if you get it wrong. I'm not tracking your answers. Feel free to discuss with your friends if you want to. Cool. I'll slowly start moving the mouse. Oh, nice. Good. That's great. So the way I read the question, which I wrote, I read the question like the answer is false. So I'll reread the question. Any method that uses a feature space transformation, 5x uses kernels, well, the SVM is an example where that's true, right? And of course, many of you are looking at this question in the context of today's lecture. But remember, we were talking about basis expansion and feature mappings in a much more general context several lectures ago. Right, so we were doing like linear regression, and we were using a feature mapping there. Now, you could frame linear regression as a kernel method, but you could also use you could use a feature mapping for like a neural network, like I kind of hinted at in the previous slide. I mean, you wouldn't typically do that. You would sort of learn the feature mapping in a sense, but you can always run machine learning algorithms after doing a feature mapping, and the algorithm doesn't have to be something that uses dot products. Because remember, kernel corresponds to dot product. So unless the learning algorithm is somehow building on the dot product explicitly, like the dual SVM, or implicitly, like the primal SVM, a kernel has nothing to do with it, right? A dot product is just one thing you could do in a space. But you don't have to use dot products in machine learning, right? Other algorithms don't use them. Even if you might be training the machine learning algorithm in a feature space, imagine a decision tree, right? You wouldn't typically do this, but you could first do a feature mapping. I mean, actually, no, that's not true. Like say in project 1, you're creating features. Many of you are creating features, and you might even create features on features. That's a form of a phi, and you might train like a tree-based model on that. That's not using dot products, right? And so even though a feature mapping is being used, there's no kernel being used, So I'm happy there was a bit of confusion with this one. The question is of course worded in a slightly tricky way, and that's intentional. So hopefully that clears things up a bit about the difference between feature mappings and kernels. So the key is kernel is feature mapping and dot products. Yay. Okay. So here's another one. And again, it's totally fine to get it wrong. We're at uni, we're supposed to get things wrong. We're machine learning algorithms, we have to have negative examples as well as positive ones. So eventually this will disappear. Okay, support vectors are points from the training set. This is more from the previous deck, I guess. Or are they something else? Are they not from the training set? Are they some other thing? What even are they? You know. So I could have asked you, describe what a support vector is, but it would be hard for you to do that with poll everywhere. So this is my question instead. And feel free to chat with your friends if you're not sure. Okay. Cool. This is good. These are good questions. Okay. So, the support vectors are the training examples that have non-zero dual variables. So when we go to make predictions, blah, 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 here, so the way we make predictions with an SVM, if we've trained the SVM with the dual formulation, is we don't get any W's. We get these weird lambda things, and we have one per training example. And it's only the training examples and the lambdas all have to be non-negative, like so. They can't be negative. They can be 0, or they can be positive. Now, quite a lot of them might potentially be 0. It depends on the data, depends on the feature mapping you use. But those that are 0 are ones that are sitting on the correct side of the boundary, and they're outside that sort of demilitarized zone. You know, they're outside the margin zone. They're way on the correct side of the boundary. They're off in the forest, whatever. And those are training examples that end up getting lambda equals 0. And they don't support the boundary. They're not holding it up. Because their lambdas end up being 0, and they're not involved in computing W, for example. They don't actually get used in computing predictions. Because if you look at this expression, you know, it doesn't matter what the dot product of a training example is. Oh, this shouldn't have a J here. Let me fix that. That's supposed to be the test instance. This doesn't matter what this is for examples, for xi's that have lambda I equals 0. Because whatever this is, the 0 kills it, right? So that's why support vectors are important, because they have something, they matter. It's not just a fun thing to give a name to. They're actually used in how predictions are made. They're actually the examples that matter for training. Right? If there was some noise in the non-support vectors, it wouldn't matter. That wouldn't affect anything. If I move them a bit, it wouldn't matter. Only the support vectors actually end up mattering. And so, but they are training examples. Okay. Let's go. I think I've got one more. Okay. Let's unlock this one. Okay, a feature mapping phi of x will make data linearly separable. This sentence isn't very well qualified. Say, imagine there's a the out the front of the sentence, if you like. So the feature mapping phi of x makes data linearly separable. I've given you some phi. I haven't told you anything about the data. Not a very well-designed question. I think I'd get in trouble if I had this on an exam. Yeah, which phi is this? Any particular phi and like any data set. Like I haven't told you anything and I've confidently said, don't you think a feature mapping will make this, you know, as long as I use a feature mapping, I mean, maybe one way to read this, as long as I use a feature mapping, the data will be linearly separable. Maybe that's a better way to read what I meant. I wouldn't ever ask something this badly worded on an exam. Don't worry. Okay, let's see what we've said. Cool. Well, it was a terrible question, so don't feel bad about this one. But so I think false in the sense that what I intended this sentence to mean, it's supposed to be false. So there isn't always going to be a feature mapping. Like whatever your data, you know, if I don't tell you anything about the data, there might be examples with two x's that are the same but have different y's. That could happen. I might not be measuring enough about the data. There might be latent variables or there might be noise in the y's. The y's might be random. So there isn't always going to be a phi that will make data linearly separable. Now, you know, if you read this sentence to mean the role of phi is to make the data more linearly separable, you would have been correct if you said true to that. So it depends on your interpretation. So in a sense, they're both kind of correct because it was a badly worded sentence. But the key thing that I was trying to get across is there isn't always going to be a phi that can make your data perfectly linearly separable. And you don't need one. Okay. All right. Yeah. Also, is your question, will there usually be something that will usually make it better? Yeah, so the question for those at home was, is there usually a phi that will make it more linearly separable? Yeah, I mean, usually, I mean, you could concoct a pathological data set with two distinct x's with a whole lot of examples duplicated with those x's and different y's, and you wouldn't be able to make it any better by adding more features. So it's not always going to be true that there'll be any phi that will improve things for you. But in most situations, there's something called the curse of dimensionality. And in fact, there are many curses of dimensionality. There's not just one, but curses of dimensionality tend to be around, you know, dimensions causing havoc. And a curse of dimensionality in machine learning is that if you add enough features, usually things become separable, but that doesn't mean that you want to separate things perfectly. What can happen is you start to fit noise. So that's the idea of that curse of dimensionality. But yes, usually there is. Yeah. Usually, so one way to test this. Yeah, exactly. Yeah, less biased. That's right. So you might be getting less bias, but maybe more variance by adding lots and lots of dimensions. That's right. So if you don't regularize enough, yeah. So it's one way to test this though in practice is to try a linear SVM, which is fancy for saying an SVM with no kernel at all, and an SVM with a very nonlinear feature mapping like the RBF, and just try them both on your data and then see if one gets better validation error than the other. And that will give you an idea if, you know, feature mappings might help. And usually it does, yeah. Usually linear SVM isn't the best, but it can be. Okay, so let's think about now kernelization more generally. So all of the information about the feature mapping is really stored in the kernel. We didn't need the feature mapping at all. We didn't even need to talk about it. In fact, if I come up with a bivariate function that corresponds to some feature mappings dot product, I don't even need to give you the feature mapping. I could just design kernels. So that's the idea here. let's not even think about feature mapping sometimes. Let's just think of a measure of similarity between two vectors, call it k, and we just need to check, is it a valid kernel or not? And maybe we don't even need to figure out what the feature mapping is that corresponds to it in order to check. And that's what Mercer's theorem will give us. If we can just design kernels, and if we have a whole suite of kernels, we can just swap them in and out and basically do different nonlinear mappings along with our SVM machinery. So that's the modular idea. So this is now very CS kind of thinking. Okay, so we're kind of decoupling things. So as another example of something that can be kernelized, we can sort of remind ourselves about how the perceptron learning algorithm worked. And then look at it and think, is there a way of doing this with a kernel? Okay. So nothing here is new on this slide, and this slide is green. This is all just from the perceptron learning algorithm. So there are sort of two things to remember here. One, we're making predictions with W. We're building up W, we're initializing it randomly, and then we make predictions on training examples one at a time by doing W.X, maybe plus an offset, maybe not. And then based on whether it's right or wrong, we're essentially sort of adding the X, or subtracting the X from W. Okay, and we have maybe a learning rate eater. But after a number of updates, once we've done a whole epoch, W is going to look like a weighted sum of the training examples. That's what it's going to look like. We're going to be weighting by eaters. We're also going to be, the more mistakes, after many epochs, we'll sometimes add some X's more than others. So it won't just be the same number of X's that we're adding, but we've got sort of weights, like how many times we made mistakes on this example, times the example. So eventually it looks like this. Now, the thing that I'm kind of sweeping under the rug here is the random initialization is gone. There is no plus initial W vector. But I could have written the random initialization perhaps as a random weighted sum of the examples. So if I'd done that and absorbed those initial random weights in these alphas, plus any numbers of mistakes I made on those examples in these alphas, the end result would be something like this. So the weights we get in the end are a linear combination of the data. And when we want to make predictions, we're just doing dot products. So far I've said, okay, weight vector is the solution of the perceptron algorithm ends up being a weighted sum of the data, which is a thing to remember, because all kernel methods have that pattern. The solution to the program is a weighted sum of the data, and that's what's going to be called the representer theorem in the sort of next slide or so. And then now let's look at sort of the role of dot products. Well, if I want to make a prediction, I only need to do dot products with data. And also with the learning, so I could have replaced this with a kernel if I wanted to do this in a feature space. And now let's look at the learning algorithm again, but almost like unroll it. We're kind of keeping store of all of the alphas so far, and we're updating the alphas now. So we start off with random alphas, and then as we make mistakes, if we make a mistake on an example, we kind of increment its alpha. If we don't make a mistake, we leave it alone. And that's how we're sort of building up the alphas. But you can see that the way we sort of decide this is based on making a prediction as well, which is also a dot product. So we're only using the data via dot products. And it's dot products of the training data with the training data, because we're only making predictions on the training data. Okay. Yep. So that's sort of an aside. Another algorithm where we saw dot products, where we saw the solution, the W, being a weighted sum of data. So now we're up to this sort of one of two powerful theorems in the area of kernel methods. And to prove this kind of thing, it uses sort of upper level undergrad pure maths. Okay, so if you want to do more maths and you like kind of that stuff, you know, if you do some functional analysis, kind of helps with this thing. But you don't need, but what's amazing is you don't need to know how to prove this to use it, right? Lots of machine learning people have used this theorem to design new kernel learning algorithms without understanding how the theorem works. You don't need to, because we're just using abstraction. Someone has implemented a function for us, and we're just applying the function. Okay, there's nothing wrong with that. So the representer theorem, what is it for? It's for recognizing when an arbitrary optimization problem, which takes the form of minimizing training error, for example, risk, empirical risk, that's why I've said capital E. For example, a sum of losses, plus a regularization term. How handy is that? Right? So anything sort of decision theoretic that we might do is pretty much always going to, well, not always, absolutely not always, but like it's often going to satisfy this. The representer theorem says the solution is going to sit inside what we call the span of the training data. It's going to, which is just fancy for saying it's going to be some kind of weighted sum of the training data, which is pretty amazing. So the solution could be anything, but you could have a really high dimensional space, and you could have lots of W, lots of possible Ws. You could have a really, high dimensional feature mapping, with millions of dimensions, a W that could be anything, and you could have 100 training examples. And if you think of the possible weighted sums of these 100 examples, it's not going to nearly cover even a tiny fraction of that space. But the solution W has to sit in the span of those things. It can't be anything. Okay, and I've used what's kind of wacky with the way I've written this theorem. F, the decision variable, is actually a function. It's not a vector anymore. You can actually optimize things with respect to functions. Okay, but you don't have to. It could just be a vector. I'm just being super general. Okay. So this also means that even if I have lots of parameters for my W, in theory, because I've got lots of features, I don't have to use them all. I can't even use them all. I'm only going to need as many parameters as there are data. So I could have lots of features, but it's not going to mean I need to fit them all. Another point is that kernel methods are non-parametric. So way back in like lecture 1 or so, or lecture 2 it was maybe, I think it was lecture 2, I talked about parametric and non-parametric methods. Parametric methods are ones where the number of parameters are fixed, no matter how much data you see. Like I've got D dimensions for my weight vector. Non-parametric methods, the number of parameters grows with the amount of data. So the dual formulation of the SVM is actually non-parametric because I get alphas or lambdas growing with the amount of data. But the primal formulation is parametric. So it's kind of both. Okay. Green. This is green. This is sort of analysis stuff. Okay. So this is like a technical thing. Okay. So this sort of tells us lots of things can be kernelized. And if we came up with the dual for a lot of different learning algorithms, we would end up only needing dot products. That's the cool thing. We only need dot products for a whole big class of things. And you can use the representer theorem as a big hammer, and you can come up with new learning algorithms by formulating them as optimizations, as many people have. And you can hit them with this hammer to see whether they're only going to need a dot product in their dual formulation, for example. So that's pretty cool. So we've seen some of these algorithms before. PCA we're going to see in the future, and then some of them we're not going to see, but they're super useful, like super practical things. And it's not just classification, regression, and clustering. There's a lot more to machine learning than those three things. Okay. Okay, so I'll go for another few minutes and we'll finish the deck next time. So here's an example. So let's construct kernels. So I've talked about how to recognize when a learning algorithm is a kernel method. How do we recognize when something is a kernel? Do we have to do a feature mapping first? No. So here's an example with the polynomial kernel. This is an example of a kernel, and I've kind of given you this example before. That's why I'm going to end with it. So it's okay if I go slightly fast. We don't have to only square. That's what we did before. We could raise it to any power d. And just for simplicity of this slide, I could set C to be 0, but it doesn't have to be. It could also, it's often set to 1. If I compute this kernel and expand it out, what do I get? So I can expand the dot product out and I get this, right? And I'm just raising this to the power of D. And now what I'm doing is I'm expanding this enormous monster out into instead of a product of sums, I'm expanding it out into a sum of products. So, you know, this term gets multiplied by this term, and sometimes it's multiplied by other terms. And so what I end up with is a sum over L, over L, over lots of different powers. So I'm basically sort of saying for every possible power of this term from 0 up until D, right, I can see that with the same other terms up to those powers. Right, so I'm getting this big expansion. And now what I can do is separate out the U's and the V's into separate terms. So that's what I'm doing here. So I'm now getting the U's raised to the power, and I'm getting a vector of these things, dot with a vector of these things. So this is a little bit sloppy. I should have like a transpose or something just to make clear that I'm talking about vectors. And then if I call my feature mapping that thing, now I've just got a dot product in a feature space. So this is just extending the example I had before for the second order to arbitrary D order. Okay, so that's all I'm doing. So I'm just raising the features to powers up to D, and I'm also multiplying them by each other. Right, so I'm getting all these combinations of things up to the power of D. And so that's the feature mapping. And so what you could do with this, this argument is this is a direct proof that this very simple definition of a kernel is a valid kernel because it corresponds to a dot product of some feature mapping. Okay, so that's all we need to verify that something is a kernel, like this. So this is a direct proof. But what I'll talk about next time is a whole lot of tools you can use to not have to do this, where you don't have to come up with what the feature mapping is. Okay, so that's a good time to stop. I'm sorry I'm a minute over. Have a good weekend and keep working on your projects, and I'll see you Monday.